Saturn's rings are a celestial wonder, captivating astronomers and stargazers for centuries. Their composition, origin, and longevity have been subjects of intense scientific investigation. A combination of factors, primarily gravitational forces and collisions, likely sculpted these majestic rings. In this explanation, we'll delve into the possible formation scenarios and the evidence supporting them. The nature of Saturn's rings. Before exploring how the rings formed, let's understand what they are. Saturn's rings are not solid structures, but vast collections of countless individual particles. These particles vary widely in size, ranging from micrometers to several meters in diameter. The composition is predominantly water ice, over 90%, with trace amounts of rocky materials mixed in. The rings themselves display a remarkable hierarchical structure. The main ring system can be broadly categorized into the A, B, and C rings, visible even with modest telescopes. Fainter rings like the D, E, and G rings exist as well. Intriguing features such as gaps, divisions, and spokes further add to the complexity of this intricate system. Possible formation scenarios. There are several leading hypotheses regarding the birth of Saturn's rings. Let's examine each of them in more detail. The ancient remnant hypothesis. This theory suggests the rings formed alongside Saturn during the early stages of solar system formation, some 4.5 billion years ago. Leftover material from the protoplanetary disk that gave birth to Saturn might have coalesced into its ring system. This scenario is problematic, which is collisions among ring particles over such vast time scales should have dispersed the rings or caused them to become contaminated with a higher proportion of rocky material is observed. The shattered moon hypothesis. This relatively recent and favored theory proposes a more dynamic origin. In this scenario, one or more of Saturn's icy moons ventured too close to the planet. Saturn's powerful gravitational forces, particularly the tidal forces, literally ripped the moon apart. The resulting debris field eventually formed the ring system we see today, which support this idea, demonstrating how a collision or a close encounter with Saturn could destabilize the moon's orbit. The cometary disruption hypothesis. Similar to the previous theory, this model suggests that a comet passing too close to Saturn was torn apart by gravitational forces. However, instead of a moon, the disrupted object would be a stray comet. This scenario could help explain the predominantly icy nature of the rings. Ongoing collisions. It's likely that collisions within Saturn's environment continue to shape and modify the ring system. Smaller moons within or near the rings could be involved in collisions, creating debris that replenishes or alters the existing rings. The hypothesis of a shattered moon destroying itself to create Saturn's rings has garnered significant support. Ring composition. The rings are remarkably pure in terms of ice content. This strongly suggests they formed from an icy body, like a moon, rather than the mixture of rock and ice expected in a primordial formation process. Ring mass and age. Recent studies using data from the Cassini spacecraft suggest the rings are not as massive as previously thought. This implies a younger ring system, potentially just a few 100 million years old. This timeline aligns better with the time frame for a destructive event like a moon breakup as opposed to an ancient origin. The evolution of Saturn's rings. It's important to understand that the formation of Saturn's rings is likely just one part of a dynamic, ongoing process. Here's what scientists think happens and detailed explain the formation theories. Gravitational shepherding. Small moons within the ring system or located near the edges of the rings gravitationally interact with ring particles. These moons are often called shepherd moons as they help sculpt gaps and divisions within the ring system. Additionally, they likely help confine the rings, preventing them from spreading out over time. Collisional breakup. Another hypothesis proposes that the rings formed from the collisional breakup of a larger moon or a series of smaller moons. High-velocity impacts could have shattered these moons into countless fragments, which subsequently coalesced into the rings through gravitational interactions. Roche Limit. The Roche limit, the distance within which a celestial body will disintegrate due to tidal forces, also plays a significant role in ring formation. Moons or moonlets orbiting within Saturn's Roche limit may be torn apart by the planet's gravitational forces, contributing material to the ring system. Primordial debris. Some researchers speculate that Saturn's rings are remnants of the primordial material from which the planet and its moons formed. These icy particles may have been left over from the early stages of the solar system's evolution, coalescing into the ring system over billions of years. Observational evidence. The Cassini-Huygens mission, launched in 1997 and concluded in 2017, revolutionized our understanding of Saturn's rings. The spacecraft provided unprecedented close-up observations, revealing intricate details such as ring structure, dynamics, and composition. Data from Cassini's instruments, including cameras, spectrometers, and magnetometers, have yielded valuable insights into the processes at work within Saturn's ring system. Recent discoveries and challenges. Despite significant advancements, several mysteries surrounding Saturn's rings persist. The presence of small moonlets known as propellers within the rings suggests ongoing dynamical processes that are not yet fully understood. Additionally, the role of external factors such as meteoroid impacts and interactions with Saturn's magnetosphere continues to be a subject of investigation. Saturn's rings stand as a testament to the dynamic processes that shape our solar system. While numerous theories have been proposed to explain their origin, the formation of Saturn's rings remains an active area of research, ripe with opportunities for discovery. Through a combination of observational data, theoretical modeling, and space exploration, scientists are gradually unraveling the mysteries of these celestial wonders, shedding light on the complex interplay of forces.